Hello. We're doing energetics now, so this week we're moving on to something different. So here's the outline of what's going to happen. I'm going to show you a demo sometime this week about two things that are interesting, and you can take a peek at these here, maybe pause. On the right-hand side are the things we're going to have to do, lots of calculations, so bring your calculator for the next couple of days. Okay, so energetics, obviously we're talking about heat and energy and the ability to do work or produce that heat, right? So we're using joules for this. So 1 joule is the amount of work done with 1 Newton of force for 1 meter. That's just the technical definition, but really we hear of joules all the time. We hear of calories a little bit more, but enthalpy is what we'll be talking about a lot. So the amount of energy or heat content of a substance, and the energy is stored in the chemical bonds. So it includes the kinetic and potential energy, but we have to use different measures for it. So you'll see a lot of change in temperature calculations, but we're not directly measuring what the bonds have in terms of energy storage. So here's a little quick read. If you'd like to know a little bit more about calorie and kilojoules, I'll assume that you'd like to want to read that, so you can pause there. And here on the right is a picture of a bomb calorimeter. It's a type of tool that we'll use here. Maybe not us in the lab, but it's something that we use in general to get information from. And so here are some average things that you might be finding around some fast food places in terms of kilojoules versus calories, and then some other dietary things you can see. Of course, these are obviously the tasty options and the ones that have a little bit more calories behind them. Here's another list of things that you might be interested in, just to kind of tie in the energy and where some of these things come from. If you're looking at biochemical studies or types of energy studies when you're older, this could be really interesting. And burning calories is always something that we're always looking at. What was the one I liked the most? Square dancing is a good calorie burn, and some light calisthenics. So don't hurt yourself too much. Thermodynamics. So we're looking at the study of energy and how it's interconnected and converted in between phases. And so the first law of conservation of energy, or the first law of thermodynamics, is the conservation of energy. Things cannot be created or destroyed. And there's two main kinds of energy that we'll focus on. The potential energy, so it's the energy due to position. So a lot of times that's the bonds for us in a chemical and a molecule. It's the potential to be converted into other forms of energy. And kinetic energy is energy due to motion. So it's being able to move. And so we're looking at enthalpy a lot in this unit. So delta H in the bottom here, that is going to be what we're calculating very frequently. Here's some vocabulary that you need to know based on some of the experimental things we'll look at. So the system is a part of the universe we wish to study, so a system, and then the surroundings are the other part of the system itself. So here on the right, figure 6.1, you can see that we have our classic setup where the system, where all of our chemistry is going on, and the surroundings is around it. And there's an open and closed system difference, right? So you'll be able to have discussions about surroundings that are closed, where only energy can move in and out. So look at the left in this figure, or on the right, we're open, where matter and energy can flow in and out. Exothermic versus endothermic reactions. Pause that. You can take a quick read. The main thing that I would like to show you here are the two diagrams that are going to click through. So if an exothermic reaction, we always think exo is to release heat into its environment, but really it's taking something that has a lot of potential energy in its reactants and using that energy to give off heat to the environment. And that's why it has lower energy products. Opposite for endothermic reactions, where the reactants are lower in potential energy and gain in potential energy through the reaction, and then the products themselves are of higher potential energy, so the bonds are stronger perhaps. And so this is a really great sketch, and we'll do this frequently, and I'll draw these a lot when we go through a couple of problems, just to get used to it. And you see EA there, the activation energy on the left diagram. That just means the activation energy, and we'll do that in topic 6. Here's another diagram on how to look at those. If you'd like to pause, they're really similar. And here's a chart if it's endothermic or exothermic. It's kind of interesting. You really need to think that the endothermic has to be in a more potential energetic state, right? So it has to have more bond energy. It has to be somehow stronger in this new form. In the exothermic process, it has to be going from something that's stronger to weaker. So a simple one that you could think of would be making ice cubes, right? So exothermic, we are burning off, and the ice cubes themselves have a lower potential energy now that they're solid. And in an endothermic process, the liquid has more potential energy. And so on. So you can take a look through here, some good examples, and I think we're going to do some examples of those in class with our Zoomed textbooks, just to make sure that we're doing fine. Expect an entrance question when you come in next day, just probably one from this table.